Hey, what's up, guys? This is Cheng here. So this time, LeetCode number 1916, count ways to build rooms in an ant colony. Okay, so this one is like another counting graph problem. Okay, so now we are an ant this time, and we need to build n rooms numbered from 0 to n minus 1, right? And then we also given like an expansion plan. Whereas we have for each room, in order to build the current room, we have some prerequisites. Basically, we have to build the pre-room first and then build the current one. Obviously, this is like a directed graph, right? And then the extension plan is given such that once all rooms are built, every room will be reachable from room 0, which means it's a tree, right? And then you can only build one room at once, and you can travel freely between rooms you have already built. Basically, you can travel this tree or graph freely, and as long only if they are connected, and you can choose to build any room as long as its previous room is already built. Okay, and then return the number of different orders. You can basically the different ways you can build all the rooms in, and then do a module of this, right? So what does it mean, right? So basically, you're given like a pre-room list where you can build like edges, right, for a tree or graph, right? And then based on this one, we need to find how many different ways we can build this tree. So what does it mean? It means that in our case, so for the most easy case, right? The easiest case scenario is this a chain one, right? So this one doesn't have any branch, 0, 1, 2 in this case. In this case, the answer obviously is 1 because there's only one way we can build this tree, which is from we build 0, and then we build 1, and then we build 2. So that's the only answer. And example 2 here. So this one is this one is it's getting interesting because as you guys can see now we have two branches, we have two subtree or two branch here, right? And each one is like is a chain, right? But this one the answer is 6. And why is that? Because as you guys can see from 0 we have two options, right? So we can either build 1 or we can build 2, right? And after that, right, after that from 1, let's say assume we build 1 first and then we build 2 here, and then the next one, we can continue building 2, or we can go back to build 3, right? Because basically as you guys can see at this point we also have different options here, right? Either 1 3 or 2 4. That's why the answer is 6. Okay, and then the constraint is 10 to the power of 5, right? So this is like a counting, or you can call it a combinatoric problem, right? And how can we solve this problem, right? Basically, the way we can solve it is we should start from the very basic one, and then we try to basically build the basic pieces and then combine them into a like more complicated scenario, right? And then basically this example 1 and 2 are showing us the two basic scenarios, right? So the first one is this one. The first one is the chain, right? So if it's a chain, then obviously the answer is 1, right? Then how about two chains in this case, right? So the answer is 6. So how did we get 6 here? And so this one, we have two subtree, right? Each sub or sub chain. So each sub chain has like 2 nodes, right? So we have a left have 2 nodes, and then the right we have 2 nodes. So this is the root, right? So this is the root. With this two basic chain here, this one's as if we can like freely combine those two chains together while maintaining the order, right? So maintaining the order, I means the relative position of each subtree has to be maintained. Basically, we have 1 and 3, right? So this order has to be maintained, and we have 2 and 4. So this 2 is also like needs to be maintained. But as long as those 2 like are maintained, we can freely choose where we want to put 1 and 3, right? So it's as if we have 4 slots in total, right? And then we can freely choose basically to pick 1 3 or 2 4 into any of the 2 locations, but where the order matters, right? Basically, we can put 1 3 here, or 1 3 here, 1 3 here, right? And then either 1 3 here. Basically, we can try put all of them together to any of the 2 locations where while the order of the relative order of these 2 are maintained. And this is what's this, guys? So this is exactly the combination, right? So what is it? That's like a C4 2, right? Where we have 4 spots, and which we need to find all the combinations where for 2, right? If we have another one, let's say 5 and 6, right? In this case, similar, right? What we'll have, we'll have like now we have 6 slots in total, right? And then we need to basically get C6 3, right? And that's how we get this 12, because C4 2 equals to what? Equals to 4 times 3 times 2 times 1 divided by 2 times 1 times 2 times 1, right? So I think you all know this, and that's where we get 6, right? And yeah, so that's how we get 6 for this very basic case, right? And this one is the basically we only, and since the left and right, there's only one way for left and right. That's how we get C4 2. How about a more like complicated scenario? Because this one is only 1 and 1, right? Let me try to use a blackboard. This is the current, this is a root, right? Again, now we have a left, right, and then we have a right, right? So this one is like another subtree, something, right? This one is another subtree. Remember, so the previous one is it's a very basic one, because basically the left one and the right one, they are both a chain. That's why we have this kind of C L plus R of L, or either R. They're equivalent, right? But because this one, the both L and R only has one way of building L and R. But what if this is more complicated case? Let's say what if they're like W1 ways to build L, and then W2 ways to build R. Then what's gonna be the final result for this R? Right? Still, right? Basically, for each way, for each combination of W and W1, W2, we have this many of ways, right? But if we have left, we have W1 way to build L, and we have W2 ways to build R. Then so we simply multiply all them, both of them together, right? Right. So basically, this is the combination for the ways of the W1 for the left tree and right tree, right? So here we're selecting all the possible left tree and right tree, and times for each combination for the left tree and right tree, we have this many of ways to build, right? So that's why we have all these three to multiply together for this more complicated case, right? And yeah, so how about that? No, this is like now we have a more complicated scenario. What if like a more complicated? What if this R has like instead of L and right, we have another one. L right and and k. Well, what if we have another subtree here, right? So this one also have like some like subtree. Now this one has a W3, right? And this one has like basically has k sub nodes here. And how can we calculate this scenario, right? So the way we calculate this one is basically we're trying to calculate into two subtrees one by one. We can pick any of them. Let's say we pick these two first. Obviously, we already have the answer, right? Of this one, right? So that's the answer for calculating, basically for merging these two subtrees. Now we have a third one, right? So for the third one, obviously this two will be different because now we have the final answer, right? The answer will be the answer. This is the answer, right? And then we'll use this answer plus the L plus R, right? This is going to be the total nodes of this part, right? And now we're treating this part as one of the subtree, and we are trying to merge it with the new subtree, and we use exactly the same expression or formula here, right? So now this one's going to be let's say this one's going to be merged. Let's say M1, right? So the total weight of this part is M, right? And the nodes of this one is what? Is M. Let's say this one is like a weight of 3, W3, right? And then here we have the total of the nodes. What's this one? This is the M, right? M equals to the L plus R, right? So this, after merging this one, we have this weight 3. Now we can use this one to merge with the next subtree, which is now we can have like W3 times, oh, this one is W3, okay. Maybe I should use W4 here, okay. So we have W4 times W3 times C of what? This is M plus K of K, right? Or either K or M. This one is fine. Okay, so now this is our plan, basically to build the tree, right? And in order to do that, as you guys can see, we need two values here. First one is the total nodes for the subtree, including the current one, right? And the second one is the answer, basically. It's a ways. It's a ways of to build the subtree with the current node as a root node. And yep, I think that's the plan, right? Cool. Let's try to start coding then. Oh, and one more thing. Actually, this thing, basically the C L plus right of L, right? So this part, this is gonna be like the factorial of L plus R, right? And then divided by, basically it's nk, it's not like nk, right? It's gonna be the n factorial divided by n minus k, right? Factorial times k factorial, right? How many nodes we have? We have a 10 to the power of 10 to the power of 5. So if you're doing like 10 to the 10,000 factorial, this is way too big, right? So we cannot simply blindly do the factorial of this of the n. So instead, we should do a modular on top of it. Basically, this is a trick to calculate a big factorial numbers. Basically, we'll use like the factorial plus the inverse of the factorial plus the modular to help us get the correct answer. Basically, we have to use this one to get the modular, right, of the big number of the factorial. And all right, I'll explain a little bit more while we're coding, but I'm not going to prove that. Basically, you guys just have to know how to do this thing. Okay. So first, let's try to build a graph first, right? We have a current, and then we have pre, right? Enumerate pre room, right? So basically, the index is the current, and the value is a pre, right? In this pre room list here, and then we have a graph. Oh, the graph is like this. Graph is going to be default dictionary of list, right? So this is a graph dot pre dot append of current. Okay, so that's how we build this graph here. Now for the DFS, so this one we don't have to use. There's no need to use the let me see. Is there a way we can use DP here? Let me think. Uh, Probably not, because in order for us to uniquely identify a case, right? So let's say we have a DP of DFS of the current node, right? In order for us to get the exact to uniquely identify this thing, right? Let's say for a subtree, basically the same subtree will give us the same answer, right? So let's say if this node has like two branches, basically the tree has to be exactly the same for us to get the same answer. Even though it's possible, let's say we have this one, we have a left. This one has a left subtree, right? And then we have a right subtree. Basically, this left and right, this two subtree, they could be the same, right? So if they're the same, actually the answer we're getting from this left and right, they are the same. So theoretically, we can somehow memorize this. We can memorize this subtree result so that we don't have to recalculate it. But the problem is that at this level, at either this left or right subtree root level, we don't know what's this tree looks like, right? Because this one maybe has like two or three childs, and this one we have to know basically the entire structure of the tree. And only when the entire structure of the subtree are exactly the same, then we can memorize the result, right? Because if they have different branches, obviously if we use that formula to multiply everything together, the answer will be different, right? That's why it's going to be hard for us to memorize that, because we don't know the state when we visit this root node. That's why I guess it's hard for us to use DP here. And cool. So for this DFS, right? So like I said, we need to return two values, right? So this one returns what? Returns total ways, right? To build subtree, to build a tree as current with current as root, okay? And the total node counts of the subtree. So this is the two things this DFS will be returning. So obviously we have a base case. Base case is that when this node is a leaf node, right? When it's current, then we simply return 1, 1. Because at this moment, if this is a leaf node, there's only one way to build the subtree, and the total count for the subtree is also 1. Okay. Then we just need to simply like merge the subtrees one by one, right? And in order to do that, we have ways, right? So at the beginning, the weight is 1, and I have another current node count, right? Starting from 0. Okay. Now for the neighbors or for the child, right? Let's call it next. Next or child. Child in graph current, right? And then what we have? We have this DFS. We have the DFS of the child, right? So DFS of child will give us what? Will give us the two things: subtree weights, right? And the subtree node count, right? So this is the two things we can get from the DFS. And then with these two things, let's remember we're gonna try to merge this tree one by one, right? So the first thing is the combination, right? So we have combinations. What is a combination? The combination is like the it's going to be the current node, right? So the current node is the previous node, right? So let's say we have three subtrees here. So this is a tree 1, tree 2, and tree 3, right? So when we're trying to merge this one with these two, we're gonna need the basically this current node will be the are the node count that we have currently we have already processed. That's why to merge with the current one, right? We have to do a combination, right? So this one is going to be a combination of the. So here I'll just how should I write this one? It's going to be a C of, okay, I'm writing a pseudocode here, and now later on I will just implement this part. So it's going to be a C of current node count, right? Actually, it's a factorial, right? Factorial of the C plus the subtree node count, right? And then we divide it by the factorial of the of the current node, right? And then also divided by the factorial of the subtree code count, right? So this is it's a C L plus right of L part, right? That's a combination. And then the weights, right? So once we have the combinations, based on if we have like different ways to build two parts, we have to multiply everything together, right? Which is the first ways is this, right? And then the second part is the ways to build this the tree we're trying to merge. And then the last one is the combination, right? Basically, for each of the combination of the current to build the current part and the next subtree, we have this many of ways to merge these two. Okay, that's that, right? And then later on, don't forget to increase this node count by the subtree count, because we have already merged this one subtree. Now we're ready to do the next one. Okay, right? And then in the end, we return the weights, right? That's the total weights to build the current subtree and basically total nodes. So total node is going to be this one plus one, right? The plus one is like including the current one, right? So the reason we don't do one here is because at the beginning, we don't have anything to basically to merge the first one, right? This combination should be one, right? That's why we have this one starting from 0, and then we do a plus one in the end, because at the beginning, if there's nothing to merge, if that's the first subtree, and then the factorial of this one should be the subtree count itself, right? So this one should be 0, right? 0 plus 1 should be itself. That's why we set this one to be 0, and then later on we add 1 to count this node itself. Yeah, and that's the main structure. And then in the end, we simply do a DFS of right? DFS of 0 and then 0, right? Because here the first one is the weight we're looking for, right? Now, like I said, right, the only problem here is that how can we solve this part? Like I said, this one is going to be too big. The common ways of doing this is going to be doing the factorial. We're doing an inverse factorial with the modular, right? And I'm simply going to just implement that here. I don't quite remember the explanation for this one. I just know how to do it. So yeah, privy room. Okay. So like I said, you guys all know the factorial, right? So the factorial gonna be the starting from 0, right? And then this n, right? And then the factorial 0 will be 0 equals to 1, right? So that's the first one. And then we need the like inverse of the factorial. Gonna be n as well. So the inverse factorial equals to the power of, at the beginning is 1 because that's the corresponding value of the factorial. And then we do a modular minus 2 and then a mod. That's how we do an inverse in factorial. And then we do this thing, we populate all everything starting 1. Obviously this one is pretty straightforward. I times factorial of I minus 1, right? And then we do a modular of mod, okay? And then the inverse of factorial is going to be the I dot power, similarly as above, the factorial of I dot mod minus 2 and then mod. So as you guys can see now, since we have the modular here, no matter how many times we do a multiplication here, the factorial and the inverse factorial will be in the controllable range here. And the reason we need the inverse factorial is because now this n factorial divided by k factorial will becomes to the factorial of n times the inverse factorial of k. Okay, basically this is the way we are converting this one into this, and with the modular, the final result will be small enough to fit in the integer. And you guys just need to remember this, right? So now, as you guys can see, now every time when we try to do a factorial divided a factorial, we can convert this one into a factorial times the inverse of the factorial of this part, right? So now this one will becomes to what? So this one is still the same, but this division should becomes to the multiply, right? So this one will be the inverse of the factorial, and this one is as well, right? And inverse factorial, right? And I think it's better for us to do another modular in the end, okay? Because this one, even this two, everything is within the modular, but if we do a multiply with the 3 numbers, we should also do a modular here. And the same thing for here, right? We should also do a modular here to make sure the final answer is within the modular range. Yeah, I think that's it. Right, so if I do a run code here, did I? Okay, does not support item assignment. Oh, this one here, I know. Should be inverse factorial 0. Yeah. Pre-rooms, a pre-room. Okay. Okay, accept it, run it. Cool, it passed, right? I mean, this one, I think time complexity is the total number of the nodes, right? Actually, Yeah, the total number of nodes, because we have DFS. We're gonna revisit each node once in this case, and then we're gonna do some factorial here. Yeah, I mean, so that's it for this problem. I think it's pretty difficult. At least for me, I, I was having a hard time doing this kind of factorial and component combinatorics problem, because for me, I think the math and this part is sometimes it's tricky. I knew how to do it, sometimes, but I just forgot how to do it correctly. you know. So for this one, just to recap, right? So for this one, the way we're solving this problem is that we start from the very basic case, which is the single chain one, right? The single chain case is like that's the base case, or at least that's the part of the base case where we have a chain, which means we only have one way. And then we go to the more complicated case here, where we have two subtree, where each subtree in this case only has one way on each side, but the nodes is different. So in this way, we simply just have this combination like C22, C42 for as the final answer, right? But then we're like expanding to a more complicated case. Let's say in this case, this one has like way one to build this left subtree, and this one has like way two to build the right subtree. In this case, we have to multiply these two together, because this way one times way two will give us all the possible combinations, right, for the left tree and subtree. And for given left and right subtree combinations, we have this many of possible ways of like inserting, basically to building those nodes. That's why that's the answer to merge two subtree. And the last case is the third one, right? What if we have another one here? Right? In that case, we have to basically merge merge them one by one, and then we use the previously merged result to merge the next one, and then in the end we get the final answer here, right? And then the last thing is this factorial thing. We have to use inverse factorial here. Actually, I believe in Python there's like a shortcut here. I believe in Python there's like built-in functions where you don't have to do this thing here. You can just use the I guess it's something like math or something. Let me think. I think it's math combo. Yeah, there's a combo function here where you can just use the this two of this one. Yeah, I guess you can simply just use this if I'm not mistaken. Let me try it. Okay. Yeah, it also works, right? So so basically, this one is part of the math package. Basically, the Python itself implement this kind of factorial and inverse factorial for you. Yeah, I'm a little bit curious that like the which modular it used. Seems like it used the same modular here for this combination, because here it doesn't pass in this modular here. I'm assuming it used the same modular value here inside, but I'm not quite sure. Yeah, basically, as you guys can, this is one of the shortcut, but not every language has this kind of function built in. So if you don't have that in your language, probably you have to manually do this by using the inverse factorial value. And yeah, I think that's pretty much it is. Yeah, it's very interesting problem, and cool. I'll stop here then. And thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.